Welcome back to the Enolates chapter. This is slides 9 through 14. So we just talked about the three main types of enolate reactions that we undergo or most widely see. And so let's start with some examples in real life where we see these aldol reactions. For those of you guys taking a biochemistry course, glycolysis is a large part of a biochemistry curriculum, and it involves many steps that accompany the conversion of two molecules of ADP into ATP, right? And we need ATP for muscle contractions and other processes. So one of the steps involved in glycolysis is a retro-aldol reaction, which is like a backwards aldol reaction. If we go back and look at the aldol addition that we did, notice that we generated this carbonyl, CH2, carbon with an alcohol, right? This 1-3 relationship between a carbonyl and the alcohol. So effectively, a retroaldol takes glucose, and you can see in its open chain form, can you see the carbonyl in a 1-3 relationship to an alcohol? The bond that's being formed in the aldol reaction is the one indicated with that squiggle line. That's where, if we work backwards, that's the bond that's going to break. So what happens is the aldolase, which is the name of the enzyme which helps this reaction. Remember, enzymes are what organic chemists call acid catalysts, right? They're catalysts. They're not specifically acidic, but they do what we do with an H+. They can catalyze the reaction. So let's say the aldolase, is the catalyst which allows for these electrons to come down. So we're doing this backwards. And what you end up with is this molecule and the pyruvic acid, which at first aldolase is still attached to it. But you have this, it's an enol, and it's going to tautomerize to the carbonyl form, which is what we see. So the aldol between these two compounds would give this glucose open chain type molecule, but the aldolase allows for a retroaldol to occur, so breaking these two apart back to their individual pieces. The end product of glycolysis is this pyruvic acid, which is used as a starting material in a lot of biochemical processes. So just kind of show you that even there are enzymes in biochemistry named after this reaction. Another fun example of aldol chemistry in bodies is with the collagen molecules. So if you look at a collagen molecule, it has this ammonium species at the end of this very large molecule. And through oxidative deamination, this ammonium species on the carbon becomes an aldehyde. So you can think about the aging process and all the words that you hear on commercials and such about antioxidants and how they're good for you. It's because a lot of the times these oxidative processes change the molecule framework. And in this case, in this particular case, our young collagen gets oxidized over time to this carbonyl. And if you have two of these, remember that the carbonyl is in equilibrium with the enol of itself, right? And so if you, under these circumstances, have lots of these oxidized collagens, then the enol, which exists in small quantities, can act like an enolate, right? Whereby the alpha carbon is the one attacking, and what you're doing is you're cross-linking. And when you cross-link all of these very once fluid molecules, right? The fluid molecules are now cross-linked and their movement is restricted, making it tougher. That's why older animals have tougher meat, because you are cross-linking their collagen molecules. So you can see we have right here, here's our 1,3 relationship between the carbonyl and the alcohol. And then over time, it's going to do the E2 elimination to form the aldol condensation, giving us the double bond. So this is just an aldol condensation reaction, and that's happening with our older collagen molecules. This accounts for the tougher meat and why you can't extract collagen from older animals. Okay, so given the reactions that we've learned in the previous slide section, I want to now talk about a few complications, things that we're going to add on to think about when we run these reactions. Problem number 1. Let's say I have this symmetrical ketone and I add a strong base and I add T-butyl bromide. Okay, well, I deprotonate, right? Acid-base chemistry. The LDA is my strong base, and I'm going to deprotonate the alpha position. I could draw it as an enolate as well. And then I want to do an SN2. Okay, what's the problem? Why do I not observe this product? Well, if you think back to SN2, all the rules for SN2 still apply. Even though we're using, a strange looking enolate as our nucleophile, it doesn't negate all the rules of SN2. If you have a tertiary carbon bearing the leaving group, these are not good conditions for an SN2. So therefore, the enolate is not going to behave as a nucleophile. It's going to behave as a base. Instead, it'll simply act in an E2 fashion, right? E2 will prevail. And you'll get an alkene, and you'll just be using your fancy enolate as a base. That's no good, right? So if your intent is to do an SN2, please stay away from the tertiary and the secondary even systems, because that's just going to promote an E2 reaction. So the long and short of it is, quick fix, stick to primary alkyl halides. This will ensure the SN2 reaction and avoid competition with E2. Okay, that's not such a huge surprise, but it's a good reminder that, we're still playing around with the same rules. SN2 is still SN2, even though we've changed the nucleophile into a new species for ourselves. Enolate problem number 2. Okay, what if I have an asymmetric ketone? Technically, there are 2 alpha carbons, right? And they are not the same. They each have protons that I can remove. And so if I remove one of them, we'll call this A. A gives me the following enolate. B gives me a different enolate. These enolates are different because remember, when we react them, the carbon on the right for A is going to be the nucleophile, and if I made B, the carbon on the left, which is a different carbon. It's a secondary carbon versus a primary carbon. So they're both very different. And they're going to give me different results when I react them with some electrophile. So I also want to bring up one more thing. There is another option. See, this is advanced. I'm not going to test you on this, but in advanced orgo, and we do have control over this, but this is more of an FYI, because it's kind of interesting. The enolate I'm showing here, where it's technically this is a Z enolate and this is an E enolate, because the groups are on the same side, and over here the oxygen and the methyl on the opposite sides. Just wanted to let you know that that is a possibility. And in advanced orgo, we actually teach you how to make the Z enolate versus the E enolate. But aside, I'm not going to test you on that. But I do want you to recognize when there is a possibility for regio selectivity. Which carbon, which region of the enolate is going to be formed? Now, there's a quick fix to this. You have two options, right? One, stick with symmetric systems. And that's what I've been doing up until this point. I've been giving you very symmetric ketones, or, I mean, as long as it's symmetric, it won't matter which side you deprotonate because of the symmetry. So that's one option to avoid this problem. The other option you can choose is to just give it one choice. So use a one-sided system. And here are some examples of that. One-sided systems could be aldehydes because, again, it doesn't matter what the R group is on the other side. Remember, the hydrogen of an aldehyde is not alpha. So that's kind of a blocked side. It's sort of a dead-end side. That hydrogen cannot be removed. Therefore, it doesn't matter. Whatever you have on the other side, as long as it's got an alpha proton, you're good, and you don't have competition. So aldehydes are an option. Or another example of sort of a blocked side would be, you know, like a ketone where if you look, the carbon on the right has alpha protons, and the alpha carbon on the left there's an alpha carbon, but it doesn't have a hydrogen. So if it doesn't have a hydrogen, you can't remove it through acid-base chemistry. So you can block it. Here's another example of a blocked system. If I had a carbonyl with a benzene, right? Then you have two asymmetric carbons. However, the alpha carbon on the left is the only option because it has hydrogens on it, while the alpha carbon on the right is completely saturated with carbons. There is no hydrogen on the alpha carbon on the right, so you can't deprotonate it. So those are two examples of blocked systems where there's really only one choice despite the molecule being asymmetric. That is not always possible, however. So what do we do when we have an asymmetric system and let's just use this very simple case that I started with, where you have an ethyl on one side and a methyl on the other, and you really do want to control which one you get. Is there hope for us? And luckily, there is. We can actually use kinetics and thermodynamics to think about this. Let's start with our starting material. Okay, and I'm going to place that one right here, our starting material. And to emphasize this, you know what I'm going to do? I'm going to add a methyl group here. I'm going to make this a little extra obvious. Okay, so here's our starting material. All right, we have two carbons for possibility here. Oh, I want to add, let's see, an orange. Okay. Got it. Okay, so we have two alpha positions, right? The green and the orange. So let's think about this. I've already kind of defined them up at the top here. I'm gonna show you that the kinetic one is the easy. Remember, kinetic is always the easy one, and thermodynamic is always the more stable one. I'm defining them for you right here, right? So I'm telling you which one is more stable and which one is kinetic. So let's start with the kinetic. Kinetic means it's the easier one. That means that the hydrogen on the alpha carbon to the right here, in this case, is the easier one to pluck off. Can you imagine why? Well, if you said less sterically hindered, you would be correct. The alpha proton on the right is primary carbon, so it's so much easier to pluck off a proton. So we're going to say higher in energy, okay, so these are high energy intermediates, but making them is not too difficult. All right, now let's look at the alpha proton on the left-hand side in this case. There's only one hydrogen there, right? That is a tertiary hydrogen as opposed to the primary green one. So plucking off that one is so much harder to do, right? But look, if we do manage to pluck off that hydrogen, look at B. Look at what it gives us. It gives us an enolate where the double bond is what? More substituted. Do you remember Zaitsev's rule? This goes back to last semester. Zaitsev's rule says the more substituted a double bond is, the more stable it is. So I'm going to place the thermodynamic enolate lower in energy. But getting to it is so much harder. It takes a lot more energy to get to it. Why? Because it's more sterically hindered. So if we look at our energy diagram, we can see that kinetic enolates are higher in energy, less stable than thermodynamic enolates because of the positioning of the double bond. However, getting to the kinetic one is so much easier, requires less energy than getting to the thermodynamic enolate. Okay, so now let's take a look at the things we do have control of when we're in a laboratory. Let's think about conditions as they relate to the kinetic enolate. So I'm defining on the left here that kinetic enolates are generated more quickly since deprotonation is at the less sterically hindered carbon. To do this, we need short reaction times. We don't want the molecules to kind of roam around and find the best thing for themselves. We want them to do them quickly. We also want to make it really emphasized that it's a problem going after the more sterically hindered side. So we're going to use strong, bulky bases to get a short reaction time and to avoid like going after a more sterically hindered proton. So LDA, which you saw was the base with those diisopropyl groups on it, is going to be our choice. We're also going to operate under much lower temperatures. We want just enough energy to get up and over this curve, but not enough energy to get over the right-hand energy hill. We're also going to use aprotic solvents. Okay, so that's going to help us. We don't want the base to be distracted by protons. We want the base to quickly do what it needs to do. And we also want lithium as a counter ion. And the reason why is because lithium is way more electropositive than, say, sodium or potassium. And so it creates a more electron-rich anion. So in this case, we're using nitrogen, the lithium diisopropyl amide, but the nitrogen is even more electropositive because it has a super electron deficient lithium. The lithium is very electropositive, making the nitrogen even more electron rich. So if we do the reaction fast and with the bulky base at very low temperatures, we actually favor the kinetic product. So how do I get the thermodynamic product? Think about this. If I give it enough energy to get to the thermodynamic product over this huge hill, isn't that enough energy to get over to the kinetic product as well? The answer is yes. And so you want high energy, but understand you're going to make some kinetic product in the process because, of course, it's easier to strip off that proton and it's a smaller energy curve. So here are the conditions to favor your thermodynamic enolate. We're going to switch conditions now because we want the reaction to go slower. It needs time to find the more stable product and fall into this energy sink. Look at how if it goes over and falls into the energy sink, it's so much harder to reverse out. Look how easy it is to reverse out of the kinetic enolate. So much easier to come back to the beginning and over time, try to find that more stable compound. So we want slower conditions. We want reversible conditions. We want it to find the more substituted carbon-carbon double bond. So here are the conditions. Longer time frame. We want to give it some time for equilibrium. We're going to use milder, less bulky bases like sodium ethoxide. The temperatures are warmer relatively, right? We're contrasting -78 here versus 10 degrees, or oftentimes you'll see just 0 degrees. These are considered warmer temperatures. I know they're not warm to us, but trust me, they're warm for the system. We also want protic solvent. Why? Because we want to protonate, we want to encourage reversibility. So we want the carbon to be able to come back to starting material so ultimately it can find that energy sink. And so protic solvents help with that. So we're going to use things like sodium ethoxide in ethanol as the solvent so that it encourages equilibrium. And we also use these counter ions that are much less, well, they're still electropositive, but relatively less so than lithium. So you're going to see a trend. If I want to favor the thermodynamic product over the arrow, you'll see things like this. Sodium ethoxide. Oops. 0 degrees Celsius. If I want to favor kinetic, you're going to see me write this. LDA, -78 degrees. And that is a very clear signal to you. That's your blinking sign that says, oh, she wants me to make an enolate. Oh, she wants me to make the kinetic enolate. Or, oh, she wants me to make the thermodynamic enolate. So now you have control, okay? So that's how we're going to distinguish between going after the kinetic versus the thermodynamic enolate. Here's some practice for you guys to try. Notice that I'm just varying the conditions to make either the thermodynamic or the kinetic enolate. And then I'm just giving you some practice with either aldol additions, aldol condensations, or a straight out alkylation.